Hello, our topic is selective laser sintering. You can see the names of the group members listed below. My name is Ben, and I'll be doing the narration for the project. So to start with the history of selective laser sintering, it was first developed in the mid 1980s by a guy named Dr. Carl Deckard and a guy named Dr. Joe Beeman. And they developed this technology at the University of Texas. Well, the technology was developed in the mid 80s. The first actual industrial SLS printer that was commercialized became available in 1992. The brand was DTM's Center Station 2000, and it can be seen pictured on the left. So as you can see, it's a very large machine, takes up a lot of space inside of the lab. Shortly after this, in 1994, EOS came out with the EOS INT P350. Um, since then, EOS has become basically the largest SLS specialist on the market. And in 2016, they had around 3,000 units installed worldwide. However, the technology in these machines is quite a bit different from what it was in 1994. And because of this, SLS is still a relevant technology today. It's still very useful, although it's not the most popular. Largely, this is due to the expensiveness of the machines and the amount of room that they take up. Moving on to the technology concept. Before understanding what SLS printing is, it's important to understand what sintering is. Sintering is the process of forming a solid mass of material from a powder through heat and pressure. And with sintering, the material never actually reaches a point of liquefaction. In order to achieve this, the SLS printers are heated from the bottom. There's a series of printers, not pictured in the picture on the left, that keep the material slightly below the melting temperature. The reason that you need heaters is because that way the laser doesn't actually have to do as much work, and it's able to be a much faster process. The laser doesn't have to sit there and heat the material up. So the way that it works is there's a bank of powder, and the laser is programmed to move across and hit the layer of powder in a certain spot where it is programmed, and it builds up the part layer by layer, similar to typical 3D printing applications. Um, so it'll repeat this over and over. The typical layer height is usually about 50 to 200 microns. Once all the layers have been sintered and the part is complete, um, the chamber needs to cool down. The reason for this is it ensures optimal mechanical properties. However, it also ensures that the part does not warp. And then the part needs to be cleaned of any excess powder. The powder is responsible for supporting the part during printing, but the powder that is not sintered can simply be recycled. After this, companies, depending on the application, will often look into post-processing, which can mean tumbling to polish a part, or surface finishing, or painting. It just depends on the application that the company desires. The reason that SLS printing is so good and still used today is because it's very ideal for complex geometries. Um, Unlike traditional 3D printing, you don't need to build up support structures. Say for like an overhang, if you were to make that with a typical 3D printer, you would need to build up a a tower of support from the base plate. However, in SLS manufacturing, the material or the part is just supported by the powder. Similarly, you do not need cores like you do in sand casting. If you've got a hollow part, this is capable of that because it can build up layer by layer, and again, it's supported. The strength from SLS parts resembles that of an injection molded part. They have, they have very good tensile strength. SLS manufacturing also eliminates waste. In 3D printing, that support structure that I was talking about that you build up from the base plate is waste material. It cannot be used again, but the powder can just be recycled. Um, Also, SLS manufacturing improves the quality because there are no dyes that wear out like there are for other manufacturing processes. You start with a bank of powder that is sintered on a part by part basis. Moving on to application and case study. So SLS is used a lot for proof of concept models. When companies are prototyping parts, they don't want to spend a lot of money making molds. So if a company was to make an injection molded part for prototyping, they'd spend a ton of money on dies. And with SLS, that's not necessary because the engineers can just upload the design of the part they want, and it's much more flexible in that there's no mold or anything. It's just done layer by layer. So it's really good for prototyping because once you have the part, you can check the form and fit on the existing parts. And if anything needs to be adjusted, it's very easy to just go back and add whatever modifications you want to the part and reprint. Whereas in injection molding, if you wanted to change one of the dimensions of the part, you'd have to create a whole nother mold. So because of this flexibility, it's very good for prototyping. Additionally, companies will like to test the aerodynamics of their part, depending on what it is. A lot of time for vehicle testing, companies will not not use a full-size wind tunnel, but instead print a scale model and put that in a smaller wind tunnel. There's many reasons to do this. Number one, the the data that you collect off of the smaller scale model is still applicable to the larger model. So companies can save a lot of money by just renting out or even purchasing for themselves one of these smaller wind tunnels, performing the testing inside of the small wind tunnel, and then applying that to the larger model. Additionally, with SLS parts, you have more flexibility. So if you say you test it in the wind tunnel and it's not how you want it, you can reprint the part and retest it fairly quickly rather than other processes where you'd have to make a whole nother mold. Also, companies have used SLS printing for cast patterns. So if you're trying to create a certain cast part and you desire the qualities of a cast part over SLS, you're still able to use SLS to create the patterns that you use for the cast part. As we talked about in class, there's many different allowances that you need to have in cast parts. So an engineer can create a pattern um, and then go through the whole process of making a cast part. And once the part comes out, you can measure it, and if there's any dimensions that need tweaking, then you can just change the pattern right there. And say one of the specifications changed on a part you need, and now you need to adjust the surface finish. Well, you can just use SLS printing to make a new pattern with a larger allowance for machining. So the case study that we looked at was for aerospace. Um, the reason that the aerospace industry utilizes SLS printing so much is because there's a lot of test parts that go on. Additionally, um, these test parts often have very complex geometries um, and and overhangs that traditional 3D printing usually just could not handle while making a clean part. So we chose to focus on this turbine pictured on the left, and you can see these fins are complex and they have, you know, strange angles that would require a lot of support. However, through the use of SLS printing, the powder supports the fins while they print layer by layer, and therefore the supports are not needed. Another reason why SLS printing is so good for aerospace is because the parts that they produce run through a lot of iterations in the testing phase. So again, you want a manufacturing method that is very flexible and also very easy to adjust if you need. Like I said previously, if any adjustments need to be made, the engineers can simply change the design on their CAD softwares and send it over to the SLS machine and print it. SLS printing is still a relevant technology that has many applications. Other than the aerospace application, which was mentioned before, it is also used a lot in the medical field. Um, one of the more simple applications is medical packaging, which is used to transport and store, expensive and fragile medical equipment. So the materials that do that need to be strong and have a high accuracy, which SLS is capable of. It is also often used for testing like joint replacements. So designers can create a synthetic joint, print it out, and then they are able to do various tests on it, like stress testing, fitment testing, to ensure that the biomedical part that they engineered meets all the standards that they would like to. Um, because of its SLS's ability to use plastic, metal, and ceramic, they have a wide bank of materials available to them to test with. While it is typically used for prototyping applications, SLS printing does have a relatively fast print time and a low cost per part. So there are some low volume industrial applications where SLS printing is used. As long as it's not a high demand, high pace environment, SLS printing machines can keep up with moderate demand. It is also sometimes used in the automotive field for similar testing. And the technology or the manufacturing process used is sintering. So again, the material is not being actually liquefied, but just heated near that point and it solidifies. And here are a list of the sources that we used during our research. Thank you.